Good morning, students. So, how is preparation going? Hmm? Yes, students, how is preparation? Are you getting my sound? Yeah,
Yes, sir. It is going well, sir.
it's going well. Okay, good. Any pressure?
Yes, sir.
Pressure is there.
Yes, sir.
Okay. So, it's like you are able to remember whatever we are doing previously, or how it is? Like, because of pressure, what happens is you forget. Okay, because of tension, you forget whatever we have studied previously. So, it's not happening, no? Hmm? Or it's happening? You have to just keep revising it. Okay, small things are there. No, just keep revising it. Formula or two from that chapter. Just go through that, revise it, so that entire thing will come in front of you. Okay, small things. Every chapter, whatever we have done, if you can see it daily, one, two formulas, one, two, three concepts, two, three concepts from here, two, three concepts from here. So your mind is able to recollect it entirely. So just give it small things. Okay, every day, but maybe it will take half an hour. Okay, so give like 15 minutes to physics, 15 minutes to chemistry, 15 minutes to biology. Every chapter at least touch once. Okay, so what will happen is entire thing will the mind will be able to recollect it. Okay, all right. So let's go for day 17, and we are talking about electrostatics. Okay, so 12th portion has started, and the portion which we are more familiar with because we finished it now only, we have written the board exam. Okay, so electrostatics, we know that when the charge is at rest, this chapter is all about when the charge is charge is at rest. Then it is about charges. So two types of charges we have: one is positive charge, other one is negative charge. Positive charge and negative charge. Positive charge means, positive charge we are talking about an object is having positive charge means it is having deficiency of electron. Object is positively charged means it has deficiency of electrons. Deficiency of electrons. And if anything is positive charge, any object is positively charged, then it has, sorry, positively I have written already. If any object is negatively charged, object is negatively charged, it means it has excess electrons. It means it has excess electrons. Right. This is how we do positive and negative charges. Then what more we can say about charges? We all know this. Actually, the positive charge means number of protons are more than number of electrons. And if this is there, number of electrons are more than number of protons. Right? So this is how we say that any object is charged or not charged, or positively charged or negatively charged. Okay. Then what more we know about charges? So charges we say is in fact a charge. Charge in as such is a scalar quantity. Okay. Charge is a scalar quantity. Right? Not a fundamental quantity. It's not fundamental quantity. Right? When any object is charged, definitely there is mass change in that object. Okay. Charging of an object is associated with change in mass of the object. Right? Charging of an object is associated with change in mass of the object. Change in mass of the object. Right. If it's a negatively charged, mass increases. Okay. If object is negatively charged, its mass increases. Okay. If object is negatively charged, its mass increases. That means if object is positively charged, its mass decreases. Okay. If object is positively charged, its mass decreases. Okay. Its mass decreases. Then what we know? Charge is quantized. Charge is quantized. That means charge on any object will be in whole number multiple of charge on electron. Q equal to plus minus Ne. Plus mean when plus? When you are removing the electron from the object. Negative when you are giving the electron to the object. So Q is equal to plus minus Ne. Then what more we can say? Charge is conserved. Okay, we cannot create the charge, we cannot destroy the charge. Why? Because the charge is a property that is associated with subatomic particles. Charge is a property which is associated with elementary particles like electron and proton. Okay, so that's why charge is conserved. Only you can transfer it from one object to the other object. Otherwise, the total charge, if you are going to see in the two objects, from one from which you are transferring to the other, then the total charge is always zero only. It is conserved because every object in this universe is neutral. Okay, so charge is conserved, charge is quantized. Then what more we have? One more property is charge is invariant. So that also I am writing here. Charge is invariant. That means charge does not change with speed. Okay, charge does not change with speed. Positive charge repel each other. Positive charge, negative charge attract each other. Okay, and negative also repel each other. So positive charge repel. Positive charge, negative charge attract. Negative charge repel. Okay, so this is basic information about charge. Right. Okay, this you are knowing anyhow. So I just gave you a small information about it. Okay, let's see the first question. The first question is, how much is the positive charge present in 180 gram of water? Okay, how much is positive charge present in 180 gram of water? So how to do that? Now we know that positive charge basically means he is asking us number of protons inside. Okay, why? Because he says water and water is neutral. We know water is neutral. So positive charge means number of protons. Okay, so how to do that? So 180 gram of water. Now first of all, let's find what is the molecular mass of water. So molecular mass of water is 18 gram. Is 18 gram. Okay, 2 gram for hydrogen and 16 gram for oxygen. So 18 gram. So if 180 gram of water is there, how many number of moles are there for water? The number of moles are 10. Number of moles, 180 by 18, that is 10 moles. Each mole is having how many molecules? 6 into 10 to the power 23. Okay. So number of molecules in 10 mole, 10 into 6 into 10 to the power 23. That is 6 into 10 to the power 24. Okay, atoms you can say. Now, what is the atomic number? What is the atomic number of water, you can say? Water molecule. How much is the atomic number? How many are electrons or how many are protons in each molecule? How much it will be? I think 18 only. How much is there in water? Tell me atomic number or number of electrons in water molecule. How much it is? Who is going to tell me? Come on. Number of electrons in water molecule. Come on, tell me. In hydrogen, hydrogen 1, 2 hydrogens are there, so 2 electrons. How many electrons are there in oxygen? Come on. Who's going to help me? No one is helping me.
In oxygen, 8 electrons.
In oxygen, it is 8 electrons. Sure. Okay. So if 8 electrons, then H2O means 10. 10 into 6 into 10 to the power 24. So total number of electrons will be 6 into 10 to the power 25. These many are electrons, means that many will be protons also. But what the question is asking, how much positive charge? So positive charge in H2O given is Q equal to Ne. Okay, so these are the numbers. So 6 into 10 to the power 25 into 1.6 into 10 to the power minus 19. That is the charge on electron. So 1.6 into 6 is 9.6 into 10 to the power 6 coulomb. This much charge is there. Huge charge is there. Okay. So this is the charge on 180 gram of water. Not charge. That means this much is positive charge inside it. Okay. So same is negative charge also. It is neutral anyhow. Okay. So this way we can find out what is the positive charge and negative charge on anything. Okay, because we all know that in molecule how many electrons will be there. It depends on their atomic number, but if this is water, so in this one we found out how many electrons are possible or how many protons are possible in it, right? Okay. Let's see then what it is. How many electrons needs to transfer to charge an object by minus 4 coulomb? Again, it's based on quantization of charge. What is quantization of charge? Q equal to Ne again. So this is minus 4 coulomb. So minus 4 equal to minus is there, that means you have given electrons to that. Okay. So N into 1.6 into 10 to the power minus 19. So N equal to 4 by 1.6 into 10 to the power minus 19. Right. So 4 into 10 to the power 19 by 1.6. So this is 0.4. Okay. So 1 by 0.4 means 2.5. So 2.5 into 10 to the power 19 electrons must be transferred so that you can charge an object by 4 coulomb. Right. So these are the questions based on quantization of charge. Now charging of objects. How can you charge an object? We know that first method is rubbing or friction. Okay, so if two objects we are going to rub against each other, one object with a less ionization energy, from there electrons will transfer to the other one. Okay, so one object will become positive charge, which is whichever is losing electron, positive charge, whichever is gaining electron, negative charge. Okay, so this way we can charge an object. This is called frictional electricity also. There are two examples which are given in NCERT for this one. One is glass rod and another one with silk. Okay, so when these two are rubbed, the glass rod become positively charged and silk become negatively charged. Right, and plastic rod and silk. So when plastic rod and silk is there, in this one, plastic rod becomes negative and silk become positive. Okay, so there can be a question which says this glass rod is rubbed with the silk and after that plastic rod is rubbed with the silk. Glass rod and plastic rod are brought close to each other. What kind of force will be there between them? Attraction. Okay, I'm writing the question, just see. Glass rod is rubbed with silk and plastic rod is also rubbed with silk. Both rods are brought close to each other. Brought close to each other. What kind of force is there between them? What kind of force is between them? Okay, our answer is attraction. Answer is attraction force. Okay, answer is attraction force. So that means between positive and negative charge there is attraction and negative charge repulsion, positive repulsion. But is it possible for a positive charge to attract another positive charge? Yes, it's possible. A positive charge can attract another positive charge if the magnitude of charges on the two objects is different. Not different, it means one object is charged heavily and other one's charge is negligible as compared to that. Okay, so if suppose that one charge here is having Q1 charge and other one is having Q2 charge. Okay, both are positive. And if we say that Q1 is greater than Q2, then what type of force is there between them? Attraction. So you need to be careful when assertion reason questions will be coming. They can ask you this. Maybe word will be there somewhere. So be careful with that. Okay, maybe and must be. Right. So a positive charge can also attract another positive charge, but provided there is a huge difference between the charges on the two. Now, which type of force is there which is sure test of charge of an object? Okay. So in this one only we'll write. And let's see if I can add one slide in this one in between. Can we do that? Does not look like. Okay, fine, no issues. Okay, so one question I'll add in this one. What is the question? The question is, which force is test of charge on an object? Okay, which force is there? If suppose you are bringing two objects, if they start attracting, is it a test of both the objects' charge? Answer is no. Because one charged object can attract neutral object also. So attraction is not the test of two charged objects. Then what is the test of two charged objects? Repulsion force. If both the objects are going to repel each other, definitely both are charged. Okay, attraction is not the test of two bodies are charged. So here answer is, which force is test of charge on an object? Repulsion. Okay, repulsion force between the two indicates us both the objects are charged. Okay, this is rubbing or friction we have discussed. What are the other two methods through which we do the charging? Conduction. Okay, conduction is one method and other method is induction. Conduction means what? One object is charged, you are connecting it with uncharged object. So there is a flow of charge from charged object to another uncharged object. Like this. If suppose this is having charge and this is uncharged. So you are connecting it. So what is happening from here? Charge is flowing. On this one, let's say charge is Q, and on this one then charge is Q minus Q. So still you can see that charge is conserved. Total charge is still Q only. So this body is also charged, this body is also charged. But if both the bodies are of the same size, then both will have same charge only. That means on this one there will be Q by 2 and on this one also will be Q by 2, right? If both objects are of same size. If both objects are of same size, if both objects are of same size, then charges on both will be same. Right, conduction. Then induction what? Induction, we don't touch the two objects, right? We don't touch the two objects. This one we'll move here. And induction we'll talk here. Induction, what happens? In induction, we don't touch the two objects. One object is this, another object is this. Okay, this is neutral, this is having some charge. So let's assume this is having positive charge. Positive charge means it's having deficiency of electrons. So when it is going to be closer to this neutral one, a neutral one is having enough electrons. There is no deficiency. So electrons it is going to attract, electrons will come over here. So this is the reason why if a neutral body is brought closer to a charged object, because of induction, they start attracting each other. They attract. Okay, that's why attraction is not sure test of two bodies being charged. Okay, so this becomes negative, and this side here atoms are there, those atoms have lost electrons because their electrons have moved this side. So this becomes positive. Okay, so in induction, first thing we do is we create polarity. Create polarity or polarization we do. Okay, create polarity. Now, is still this body charged? Answer is no. Then what to do? Earth it. What earth does? Whichever surface is connected, if there is free charge on that surface, that free charge will go to the earth. What is free charge here? Is this negative free? No, because this positive is attracting. So is this positive free? Answer is yes, it's free. So then what will happen? This positive charge will go into earth. We can say like that, but actually positive charge never flows. What flows is electrons. So electrons will move from earth to this surface and this neutralized. This surface gets neutralized here. So negative will come here, negative will come here, negative will come here, negative will. So this plate has got negative charge because earth has given it electrons. So what will happen to this? This becomes negatively charged. Now you remove the earthing, take it over here. Now this is negatively charged plate. So this is how induction is done. How the charging due to induction is done. Okay, with the help of earth. Okay. Then what is the redistribution of charge? That means this is related to conduction. Now what's happening? What's happening in this? As we said that if two objects are there, both have same size. If both have same size, if this is Q and this is neutral. Okay, and we are connecting them. Then what will happen? This will also become Q by 2 and here also will become Q by 2. Okay. If suppose we are having more than 2, then what? If suppose we have one is here, another one also we can make. here. One more we can make, it's here. Okay. So first, let's say we are having this as charge on this is q and charge on this is q by 2. Okay. Then we connected them. Connected, then what will happen? We said that both will get same charge. So at the moment, what is the charge on them? 3q by 2. So what will be there then? This will become 3q by 4 and this will become 3q by 4. Now suppose that this is also having some charge. Let's say this is also having 2q charge. Okay, and this we are connecting now with this one. Then on this one, how much charge is there? 3q by 4. On this one, what is there? 2q. So what will happen? 3q by 4 plus 2q is how much? 3q by 4 plus 2q is 11q by 4. So then they will have equal charge again. So here will be 11q by 8 and here also will be 11q by 8. So like this, redistribution of charge takes place if you are going to connect them, either touching them or connecting them with the wire. Okay, provided they are of the same size, remember. Okay, so this has got redistribution of charges. Okay. Alright, so this is redistribution of charges. Now we are moving on to Coulomb's law. Coulomb's law is what? We all know that if there are two charges, Q1 and Q2, kept at separation R, then there is a force between them, which is 1 by 4 pi epsilon naught, Q1 Q2 by R square. Q1 is applying force on Q2 and Q2 is applying force on Q1. Both are equal and opposite. So that's why it is told that electrostatic force is action-reaction force. Action-reaction force. Okay, because it's acting on both objects. One object we can call action, other one is called reaction, and its magnitude is equal to this. Okay, its magnitude is equal to 1 by 4 pi epsilon naught Q1 Q2 by R square. This epsilon naught here is permittivity. Epsilon naught is permittivity. Permittivity of free space. It has got value 8.85 into 10 to the power minus 12. Okay, its unit is what? Take epsilon naught here and bring F here. So Q1, Q2 means Coulomb square by Newton meter square. So Coulomb square by Newton meter square is its unit. And from unit we can very well find out what is its dimensions also. So Coulomb means ampere second square. Newton means mLT minus 2. Meter square means L square. So we have dimensions. M to the power minus 1, L to the power minus 3, A to the power 2, T to the power 4. These are the dimensions of epsilon naught. Permittivity. Okay. So electrostatic force is action-reaction force. Then what else we can say? We can say that electrostatic force is the central force. Electrostatic force is a central force. Central force means it always acts along the line joining two charges. It always acts along the line joining two charges. Okay, then what? Line joining two charges means what? The force on Q2 will be like this, in this way. Force on Q1 will be like this. So I am just removing this. Okay, that thing is removed. Alright, so this is how the force acts. Then what we can say, it's a conservative force. It is a conservative force. It is a conservative force. Conservative force, we are very well aware of that the work done by these forces is equal to, or rather, dependent on initial and final position, and they are not dependent on how the object has moved from initial to final position. Okay, only initial and final positions are enough, right? So it's a conservative force also there. Then what more we can say? It's a central force also we said. Then one of the more important property is, what it says is, force exerted by one charge on the other is independent of the presence of third charge, That means if three charges are there, Q1, Q2, Q3, then force of Q1 on Q2 has nothing to do with Q3 charge. Net force on any charge is going to be different. It will be affected by the presence of any charge, net force. But force because of Q1 on Q2 will not be affected by any number of charges present nearby. Remember that. Okay. So these are the important properties as far as force is concerned. We know that it follows superposition principle. Force is a vector quantity, so it will be vector laws of addition. We know that, so I'm not writing in that one. Action reaction, it is along the line joining two charges. It's conservative force, and what it is independent of the force between two charges, is independent of the presence of third charge. Okay, so let's move ahead. Permittivity. Now what permittivity is? So let's try and understand. If there is a charge Q1 here and there is charge Q2 here, separation is R, then force we are writing as 1 by 4 pi epsilon naught Q1 Q2 by R square. Now this is free space. Now the same thing if I do, same charges, same charges I take here, and here is some medium. Okay, separation is same. So now force is 1 by 4 pi epsilon naught K Q1 Q2 by R square. This is F dash. So what has happened to the force is the force has decreased. What is K? K is dielectric constant. That also we'll discuss. Okay, K is dielectric constant. Though we all know that K is dielectric constant, and K is also equal to relative permittivity, epsilon R. Relative permittivity. And what is this relative permittivity? Relative permittivity is actually epsilon by epsilon naught. What is epsilon? We can say here permittivity is epsilon. Okay, permittivity of the medium is epsilon. Okay. So that means this K I can write as like this, 1 by 4 pi epsilon Q1 Q2 by R square. So what is here in this between this F and this F dash? F dash is less than F. F dash is less than F. So because of this permittivity, what has happened? Because of this medium's permittivity, the force exerted by Q1 on Q2 is decreased. That means, is the permittivity of medium opposing the force exerted by Q1 and Q2? Answer is yes. Answer is yes. So permittivity basically is the opposition or resistance to the electric field. Okay, what is permittivity? Actually, property of the medium. Property of medium. Okay, due to which it opposes the electric field. It opposes opposes the electric field. Okay, but it is also related to induction, because when you are bringing the charge, this medium will get induced induction, right? So, how much maximum charge it can store, that also depends on permittivity. Now, suppose conductor is there. Okay, what happens to the conductor? Same charge will induce over here. Same charge will induce over here. That means what will happen? Electric field inside this medium becomes zero. Correct or not? So, permittivity only decides that how much charge can induce on that. Okay. So, charge induced on the medium also depends on permittivity. Where to write it? Here. Charge induced in medium also depends on permittivity. Or you can say that how much charge can be stored inside a medium also depends on permittivity. Charge induced in medium also depends on permittivity. And whose permittivity is least? Free space. Okay, free space permittivity is least. As you are going in any other medium, permittivity is going to increase only. Okay, fine. Now, K of conductor of metal is infinite. K of conductor is infinite. Okay, so if K is infinite, epsilon naught K also infinite. What is epsilon naught K? Epsilon value. This is epsilon. So, epsilon is epsilon naught K. Okay, so conductors K is infinite, so epsilon also is infinite. This is permittivity. Okay, and sometimes they will be asking you relative permittivity. So, relative permittivity you can also say, because it's epsilon by epsilon naught. So, in terms of F and F dash also we can define it. Okay, what it will be? If in terms of F and F dash I have to define it. Okay, so see now, if I say, just remove this in the moment. First, let's say that what is F by F dash? You say 1 by 4 pi epsilon naught Q1 Q2 by R square, whereas F dash is 1 by 4 pi epsilon Q1 Q2 by R square. So this and this gets cancelled. Okay, now 1 by 4 pi epsilon naught by 1 by 4 pi epsilon. That means this becomes epsilon naught, both places I have written. Okay, so 4 pi epsilon by 4 pi epsilon naught equal to F by F dash. 4 pi cancelled. So epsilon by epsilon naught. What is actually epsilon r? Epsilon by epsilon naught only. So relative permittivity is also F by F dash. Okay, F by F dash. F dash is what? Force in medium. F is what? Force in free space. Right? Okay. So here is a question. Okay, where a third charge Q to be placed so that net force on it is 0. Okay, two charges Q and 9Q is given. Okay, this is related to equilibrium of charges. So Q and 9Q given, and you want to place another Q somewhere so that net force on it is 0. So what we say in this case? We say that if the two charges given are like charges, then third charge definitely has to be placed between the two. Not in the middle, we are saying between the two we have to place. Okay. So if two charges given are like charges, then new charge need to be placed between them for 0 force. And if they are unlike, then you have to place it outside the line joining two charges. Okay. If two charges are unlike charges, then the new charge must be placed outside the line joining two charges. Okay, this we'll remember. And the second point is this third charge need to be placed closer to smaller charge. Third charge, this Q, need to be placed closer to smaller charge. Okay, Q need to be closer to smaller charge. Okay, so if it is need to be placed closer to smaller charge, means that means somewhere here. So we'll say, okay, this is X and this is R minus X. Okay, then let's find the force. Now you can see that force because of this Q charge is in this direction. It's a repulsive force. This 9Q is also applying repulsive force on this, which is in this direction. So both can cancel each other, or both are equal, then they will cancel each other. So equate the forces. So we'll say that, okay, 1 by 4 pi epsilon naught Q by x square equal to 1 by 4 pi epsilon naught Q 9Q by R minus x whole square. This cancelled, this and this cancelled. What you have here is 9x square equal to R minus x whole square. So this is 3x equal to R minus x. So x equal to R by 4. Okay, we have to place it at R by 4, and this obviously will become 3R by 4. So this way we can find out where exactly the force on third charge can be 0. Okay, fine. One more question is there. Q1 and Q2 are placed at a separation of R. This is free space. And then Q1 and Q2 are kept in a medium of dielectric constant K, and this separation is X. So what question is asking? If force between charges in two medium is same, find X. Okay, simple question. So, okay, fine. So force is same. We are saying F is equal to F dash. F is what? Again, 1 by 4 pi epsilon naught Q1 Q2 by R square, and here is 1 by 4 pi epsilon naught K Q1 Q2 by X square. This is and this is cancelled. 4 pi epsilon naught cancelled. So what we have? R square equal to Kx square. What is asking? X. So X is equal to R by root K. Okay, X is equal to R by root K. Just a moment. Okay. What this is? QA and QB. We have given charges on these two spheres. Here QA, here QB. And identical two more spheres are there. This is uncharged and this is having 2 QB charge. Then what question is asking? Find force between first two spheres at separation R. Okay. These are the first two spheres. First two spheres. Okay. So what we did? We touch with this one, with uncharged one. So what will happen? We know that both will have equal charge then. Then here charge is QA by 2 and here charge is QA by 2. Okay. Here is what? QB and 2QB. So here charge will become 3QB by 2. And here also 3QB by 2. Now he is asking what is the force between them if the separation is R. Fine, no problem. It's an easy question now. force is 1 by 4 pi epsilon naught QA by 2 into 3 QB by 2 by R square. That's it. Done. Okay. Then what next? Okay. So this is a regular polygon. Okay. It looks like a square, or it may be a rectangle also. So it's a regular polygon. In this one, charges are placed at all the vertex and force is asking on the charge placed at center. We know it's 0. Okay, this is repelling like this. This is repelling in opposite way. This is like this here, and this is repelling like this. So this is cancelling this, this is cancelling this. So net force is 0. We know that. Is it going to happen in all regular polygon? Answer is yes. Okay. Even if it is a pentagon, yeah. Even in pentagon, the same thing is going to happen. Okay. If it's like this, this Q, this is Q, this is Q, this is Q, and this is Q. And you are keeping it at center. Okay. So force on the charge at center is still 0. Any regular polygon, it will be 0 only. Right? Fine. So in any regular polygon, force on charge at center, force on charge at center is 0. Okay, but they ask you the question in different way, right? They don't ask direct question on this one. They ask that by removing one charge, what will be the field, or rather the force. Okay, remove one charge. Okay, let's remove one charge from here. So it's like this now. Okay, charge on this one is Q, charge on this one is Q, charge on this one is Q, and you have to find the force on the charge at the center. And here nothing. So what we do in this case? This is A, this is B, this is C, and this is D. Okay, so we say in this case what is happening? We say that force due to charge at A plus force due to charge at B plus force due to charge at C plus force due to charge at D is equal to 0. Where? Force at O. Due to all this it's 0. So we know that force due to A plus force due to B plus force due to C is equal to minus of force due to D. Okay, if I say that this is A, this is B, this is C, and this is D point. So he says that Fa plus Fb plus Fc actually is equal to minus Fd. That means if in place of these three, I place only one charge at D, it will be equal to that. Okay, listen again. Fa plus Fb plus Fc equal to minus Fd. Okay, so in place of these three charges, or rather the sum of these three charges is equal to the force only due to charge placed at D. So let's place here the charge. Let's place here the charge, and whatever force will be coming, that's our answer. Okay, so I am placing here charge Q. Hypothetically, it's not there. So here is charge Q, and I am going to find force due to this alone. So what will be answer? 1 by 4 pi epsilon naught Q square. Okay, and if the sides are A, then I know that this will be A by root 2. So A by root 2 whole square. But he says minus. That means the direction will not be repulsion, it will be attraction. So this is our answer. Okay, so we have to remember this, then only we can find it easily. Otherwise, we have to find force due to each and every charge and add it. We don't have that much time. Okay, the concept says sum of this, this, and this is equal to force because of this charge, but taken in opposite direction. Remember that. Okay. Then what else? And we have electric field. Electric field is what? Electric field is a region around the charge in which the electrostatic force due to a particular charge can be experienced, right? So electric field is something like this. Suppose like this it is. And here is charge Q we are keeping. So because of this charge Q, you can find the force of this charge Q within this field. If you go out, this Q charge is not going to apply any force on you. But when you come inside, it will apply force. Okay. What is its magnitude at any moment? We call that magnitude as electric field intensity. Okay. And what is that? If you are bringing the charge over here, suppose Q charge we brought, and this is separation R, then electric field is electrostatic force applied by this charge on this one by Q. Because its electric field should not have anything to do with this charge. It's electric field, not electric field of this charge. So it should be independent of this charge. So what we have said that it is the force experienced by this charge or force experienced per unit charge. Okay. Electric field is force experienced per unit charge. Experienced per unit charge. It's a vector quantity and its direction is same as electrostatic force on this charge. Okay. How we measure it, how we calculate normally? Normally we say that we are not bringing Q charge, we are bringing positive 1 charge, a unit charge. So whatever is force on plus 1 charge, that is only the electric field. Okay. So electric field is force on unit charge. This is how we calculate our electric field intensity. Okay, equal to F by Q. And how we show the direction? Direction of electric field we show with electric lines. So here at the moment, what is the direction? We said that it is having same direction as that of a force. So on this Q charge, it's a repulsion force. So keep here positive 1 everywhere and see that how it is. So we will say that here also repulsion, here also repulsion, here also repulsion, here also repulsion. Okay, so then electric field lines. Electric field lines are what? Hypothetical lines used to show the direction of electric field. Hypothetical lines used to show direction of electric field. Direction of electric field. Now, as we said, positive charge is here, then electric field will be outside it like this. And if negative charge is there, what negative charge is going to do to positive one? It's going to attract. So negative charge direction is like this. It's like this. Okay, you all know positive, negative are close together, then what happens? Well, how will be the electric line? So if positive is here and negative is here, then how it will be? It will be from positive to negative. So electric lines of force move from positive to negative charge. Okay. Same way here also. Something like this. Okay. So electric lines of force move from positive to negative charge. Electric lines move from positive to negative charge. If negative charge is not there, then they move towards infinity. Like if the charge is placed at infinity, then how we get the electric lines? Straight lines, parallel. Okay. So parallel means is, are they converging anywhere? No, they are going to infinity. So if electric lines move from positive to negative charge, or they move to infinity, right? Then what more we can say? If density of electric lines is more, density of electric lines is more. It indicates intensity of electric field is more there. If density of electric lines is more, it indicates higher intensity of electric field. Higher intensity of electric field. Okay, higher intensity of electric field. Alright, then what more are there? What more points we can say about electric lines? Electric lines always move from positive charge to negative charge, we already have said, right? Then, more number of electric lines associated with any charge means is charge is also more there. Or we can say that ratio of charge, ratio of two charges can be determined by ratio of number of electric lines, linked with charges, Okay, that means Q1 by Q2 we can say is equal to N1 by N2. N1 and N2 are number of electric lines. Now here 1, 2, 3, 4, 5, 6, 7, 8. Here 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7. Here is 1, 2, 3, 4. 1, 2, 3, 4, 5, 6, 7, 8. So if here is Q1 and here is Q2. Okay, so we can say Q1 by Q2 is equal to 8 by 7. We cannot find exactly how much is the charge, but we can definitely find what is the ratio of charges. Okay, if two positive charges are very close to each other, then how will be the lines of force? It will be like this. Okay, like this here. And this point here, we call as neutral point, where electric field will be 0. Okay, like this. We found a little while ago, where shall we keep one charge so that the net force on this is 0. This is only that. It's called neutral point. Okay, so this is electric lines of force. Then electric lines of force, there are certain objects whose electric lines of force we should remember. Okay, that we will see in Gauss law. Okay, and there also I will tell you electric field due to ring, that we should remember. Okay, formula we should remember that. Right, we have seen that in gravitation also though. So just I will tell you what is the electric lines. Okay, electric field due to a ring. Okay, here only I will tell you. This dipole. So ring is here. Okay, uniformly charged at distance x. Okay, how much is going to be the electric field intensity at distance x? Okay, and what will be the direction? The direction will be along the axis only. Direction is along the axis, E value. And what is this E? 1 by 4 pi epsilon naught Qx by r square plus x square to the power 3 by 2. Okay, in gravitation we got gmx by same thing. Gmx by g into mass of the ring into x by r square plus x square to the power 3 by 2. Here it is in place of g 1 by 4 pi epsilon naught in place of mq. That's all. The remaining all is same. Okay, so qx by r square plus x square to the power 3 by 2 is electric field, and otherwise for point charges we know that it is F by Q. So whatever force is there per unit charge is the electric field value. Okay, so whatever questions we did for force we can do also for electric field. right? Then we were on the dipole. So dipole is here. And dipole is what? When two charges equal and opposite are kept close to each other, then this formation is called dipole. Okay, and its strength is measured by dipole moment. Dipole moment. Dipole moment we represent with P, and its value is equal to what? Q into separation between two charges. Q into R. Okay, for calculation purposes, we take this separation as 2L. So, okay, then dipole moment here is Q into 2L. Okay, here is R, so we have written QR, here it is Q into 2L. Direction is from negative to positive charge. Negative to positive charge. Okay, this is called dipole moment. It's a vector quantity. Yes, it's a vector quantity. I have marked it as a vector. Unit is coulomb meter. Unit is coulomb meter. Okay, alright. In dipole, what we do? We find electric field because of this along the axis and on equatorial plane. Okay, so electric field along the axis of the dipole. If we take a dipole here, now in this one many questions many times are asked on the dipole. Okay, so we need to be careful now with this one, and every time when they will ask question there will be some surprise in that. What surprise? Suppose this point A we want to find the electric field, and this separation we take as 2L. From the center this distance is given R. Okay, so in this one there are two cases, when R is comparable to L and when R is very large as compared to L. Okay, when R is greater than L, then we know the formula directly, that is 1 by 4 pi epsilon naught 2p by R cube. P is what? Dipole moment, 2p by R cube, and we try to apply this everywhere without knowing that whether R is greater than L or greater than L or R is compared to L. Every time we apply this and we do it wrong. Okay, latest question on dipole was when R was comparable to L. When R is just greater than L. So in that case I cannot apply this formula. I cannot. So then what formula we have to apply? We'll see that. Let's derive it once. Okay. So here let's assume that there is a positive 1 charge. Okay. So electric field we are finding at A. So what it will be? Electric field due to positive Q plus electric field due to negative Q. So what it is? Q by R minus L whole square. Okay, R minus L whole square. And this one minus Q by R plus L whole square. Why minus? Because direction is opposite. Because of minus Q, direction is like this, and because of plus Q, direction is like this. So what we are getting? Q here. Okay, so R plus L whole square minus R minus L whole square by R minus L whole square into R plus L whole square. And 1 by 4 pi epsilon naught is there. Okay, so here it is. Now what? Square them. So Q, R square plus L square, 2RL. Here is also R square plus L square into 2RL. So R square plus L square will get cancelled. What we are getting? 4RL by R minus L whole square into R plus L whole square. One by 4 pi epsilon naught as it is. Then, now Q into 2L is actually P. Then what you have? 2R by r minus L whole square into r plus L whole square. So this is P, and here is 1 by 4 pi epsilon naught. So what are we getting here? 2PR by r minus L whole square into r plus L whole square into 1 by 4 pi epsilon. This is electric field. This is electric field. Okay, not this. This will come if this is very small as compared to r is very large as compared to L. So we will neglect this L. We will say r square. Here also r square. So r to the power 4. This is r. So it will become 2p by r cube. But this is true only when r is greater than L. Otherwise, we have to do it in this way only. And on this only the question was asked last time. What was given? It was given to you that this is something like 50 centimeter. Sorry, not this one is 50. Okay. This one was given as 10 centimeter, let's say. This is 10 centimeter and this r was given as 40 centimeter. Something very comparable. Now comparable means we can't do this, we have to do this. But there was answer according to this also. We need to be careful. Then second most important point in this one is the electric field here. Now which direction is electric field? Because of positive Q, here force will be more. So direction of electric field will be this. And this direction of electric field and dipole moment, both are in same direction. So in axis, along axial direction, along axis, electric field is parallel to dipole moment. Electric field is parallel to dipole moment. That means both will be in same direction. Equatorial plane, it's opposite. Okay, equatorial plane, we have opposite thing. What happens in equatorial then? Equatorial plane, electric field will be in opposite direction to dipole moment. Okay, see then, we'll do it here. Equatorial plane. Again, in this one also we need to be careful. The answer is yes. Okay, so equatorial plane, we will say, okay, this is plus Q, this is minus Q. And we'll take point here. This is 2L. This is R. This is some point A. So if suppose R is greater than L, then electric field at A, we will say is 1 by 4 pi epsilon naught P by R cube. That's all, over. But if it is not, if it's comparable, if R is just greater than L, then what you will do? You are going to find force because of this one here. So force will be like this on positive one charge. And this one, this is going to repel it. So what will happen to resultant? You can see resultant is here. And how is dipole moment? Like this. The dipole moment and resultant electric field will be in opposite direction on equatorial plane. Remember that. Okay. Now, if this is theta, okay, and this is also theta. Why? Because this angle here and this angle here are exactly equal. Because this is R and this is L. So tan theta equal to R by L. So theta is same. Okay. So its component here in this direction e cos theta, its component is also e cos theta. So we can say that this will be 2e cos theta. This is resultant field. Okay, 2e cos theta. Then we can find it. 2e cos theta. So 2 into 1 by 4 pi epsilon naught Q by this. Now what is this? This is R, this is L. So this will be R square plus L square. Then cos theta means L by this root over R square plus L square. Now this is the value. If R is comparable to L, then this is our value. Okay, so what it is now? 2QL, which will be P 4 pi epsilon naught R square plus L square to the power 3 by 2. So P by 4 pi epsilon naught R square plus L square to the power 3 by 2. Okay, what it is when R is greater than L, P by R cube. When it is comparable, what is this? This is like this. We need to be careful. Okay, right. So this is related to electric field due to dipole, right? Okay, then we have flux. We talk about flux. What is flux? Flux is electric lines of force, electric lines associated with an area. Okay, electric lines linked with area. Phi actually is equal to E bar dot A bar. Phi is only the symbol with which we represent electric flux. So this is E bar dot A bar. So E bar dot A bar, if suppose we show area is like this, the ring's area. Okay, and electric field is like this. Okay, so what will be the flux here? Flux will be E bar into A bar. E bar dot A bar means actually EA cos theta. Now here we'll write E into A. Reason? Because area is in same direction. This is area vector. Okay, but if suppose we tilt this ring, we make it like this, not like this. Okay, so we tilt it in this way. Then, and electric field remains same direction. So electric field is like this only. Okay, electric field is in same way, like this. This is electric field. And where is area? Area vector is like this. And the angle between them is theta. Then in this case, phi equal to EA cos theta. But if suppose it's like this, okay, and electric field is like this here. This is electric field. Then in this case, what is flux? In this case, flux is 0. Reason? Here area vector is like this and the angle between them is 90 degrees. Electric field is like this, area vector is like this, so flux is 0. Okay. This is how we calculate the flux, right? Now, okay, fine. Gauss law also we can push it back. So if suppose we have a cone, this is a cone, okay, then make a cone over here. Okay, this is a cone. The radius is r and height is h. Now in this one, if you want to know how much is the flux, this is the electric field. Okay, this is how the electric field is. What is the flux? It's a flux is E into pi r square. Which flux? We'll say which is going inside. Flux going inside is E into pi r square. Pi r square is this area. Correct? This is flux. Same way, if suppose we take one sphere, okay, and we make electric field like this. This is how the electric field is. Okay, and its radius is also r. Then what is the flux which is going inside? Again, E into pi r square. Okay, because area through which it's going, it's not this area because we have to take perpendicular area. So area through which it's going is this area actually. Okay, this is the area. And this area is pi r square. Okay, so here also our answer is E into pi r square. Correct? Right? So this is how flux we calculate. Okay. Then what more we can do? Can any more questions we can solve in this one in the case of flux? Answer is yes. Which type of questions? You have seen this in even in board questions also. Very similar question. Okay. It is there in NCERT book. Values may be different. Okay. All right. Okay. So I need to make one cube here. I'll make one cube. So cube is here. Okay. It's like this. So here is this cube. Okay, side is A. And from here, let's say it is at a distance of 1 meter. 1 meter shall we say, or A only will say. Okay, an electric field is given. Electric field is given to you as, let's say, E naught x square, I cap. So then the flux is asked from us. How much is the flux linked with this sphere? Okay, rather this cube. How much is flux? This is the question. So how is the electric field? Electric field is along x-axis. Electric field is like this. Okay, electric field is moving like this here. So electric field is linked with which area? Electric field flux is linked only with area which is along x-axis. If area is along y-axis, because electric field is along x-axis, and area is along y-axis means flux is 0. If area is along z-axis, flux is 0. And all these planes of this cube are either along x-axis, y-axis or z-axis. Okay, so which area is along x-axis? This area. This area is along x-axis and this area is along x-axis. Remaining are not. In this direction, this is belongs to y, this belongs to y, and backside area z, this front area is z. So only x is this one. Okay, only x is this one. I think in this one little problem is there, right, in seeing it. So we'll just change the color of this one. Maybe make it white. What happened? Okay, white. Here also. Okay. All right. This also will make white. So that it's clearly visible to you. About the cube is visible to you. Okay. So now what is happening? From here flux is going inside, from here flux is going outside. So flux of the cube we'll say actually is, we'll add phi in plus phi out. Okay, what is phi in? So phi in means is what is electric field value at this one? Electric field value is E naught A square because this x coordinate is A. Okay, so phi in I am writing E naught A square into area is what? That is also A square. But area's direction is what? This. Why like this? Because area is always outward normal. area vector in 3D objects. In 3D objects is always outward normal. Outward normal. Okay, so this is area. So what will happen? Electric field is like this, area is opposite, so angle is 180 degrees. So E into A cos 180, that means this will be negative. Phi in is mostly negative only. So in the previous case also we should write negative, no? Yes. Here also negative, here also negative. Yes, correct. This should be negative. Phi in is always negative, phi out is always positive. Okay. Okay, so here is then, here, now this is also A. So here is also A, that means electric field value is different here. E naught into 2A whole square. This is electric field value. Into area, what is area? A square only. And this time it's positive. So what is the answer? This is minus E naught A to the power 4. Whereas this is 4 E naught A to the power 4. Our answer is 3 E naught A to the power 4. 3 E naught A to the power 4. So this way we can calculate the flux linked with 3-dimensional objects. And 2-dimensional objects also we saw already. Okay. Then we will see Gauss law. What is Gauss law? Gauss law is used to find electric field due to symmetrical objects and large objects, uniformly charged large objects, where Coulomb's law we find very difficult to apply. Okay, Gauss law helps us. What Gauss law says? Gauss law says that with any closed surface, real or hypothetical, real also we can consider as Gaussian surface, or if it is not there, then we can consider hypothetical surface also. So, electric field or flux rather linked with the Gaussian surface is equal to charge inside that Gaussian surface by epsilon naught. Electric flux linked with the Gaussian surface is equal to Qn by epsilon naught. Okay, so electric flux is equal to Qn by epsilon naught. Does it mean that this electric field is also due to Q inside only? Answer is no. This electric field is because of inside charges as well as outside charges, but its magnitude is equal to Qn by epsilon naught. Remember that always. Okay, if suppose this is Gaussian surface, if I make Gaussian surface here, okay, this is Gaussian surface, and if I frame it like this. Okay, so this is Gaussian surface, and suppose here is charge Q1, and one more charge we can keep Q2, and inside we will have Q3 minus Q4 and Q5. Then electric field which I am writing here, this electric field is because of all the charges Q1, Q2, Q3, Q4, Q5, and that's equal to what? Q3 minus Q4 plus Q5 by epsilon naught. Remember that. So this electric field is due to all the charges. Electric field due to Q1, okay, ds, plus electric field due to Q2, ds, plus electric field due to Q3, ds, plus electric field due to Q4, ds, plus electric field due to Q5, ds, equal to Q3 minus Q4 plus Q5 by epsilon naught. That is the meaning of it. So electric field is because of all the charges, but that comes out to be equal to, okay, reason is because flux due to this through this one is 0. Why? Because flux are actually going inside also and going outside also. Okay, something like this. This is our Gaussian surface, or actually closed surface also. Okay, so if any charge is outside, suppose this is charge. So if I am going to make the electric lines from this charge, So it's like this, okay, like this here, okay, same way, like this, and in between all, many will be there in between them, okay. So this is going in also, this is going out also, right. So if I assume that these lines are actually from where actually the energy is coming. Electric field is what? Energy. So energy is coming, but same energy is going out also. So how much is energy within this? No energy left. So flux linked with this surface, if the outside charge is there, is zero. Okay. So flux with a closed surface due to outside charge is zero. Due to outside charge is zero. So that is the reason why we are saying here this electric field is because of all, but that is equal to what? Flux. Flux through closed surface. So flux through closed surface doesn't depend on charge outside. So that's why here is Q in by epsilon naught. Okay, let's see about charge inside. And charge inside is here, then what? Here is charge. So its flux, you see, its flux is only going out. It's not coming in. So this energy definitely is linked with this outside surface. But here, when it's going inside, flux is negative. When it's going outside, flux is positive. When you add it, it becomes zero. Clear? Right? Okay. So if I make one question over here, same cone question only I am making. Okay. So here we'll make one cone. Okay. Here is cone. Right? Now, my question is a simple question actually. Like this is electric lines. Electric lines are like this. Okay. And its radius is r. The question is how much is total flux linked with this cone? Flux total with the cone. Answer is zero. Why? There is no charge inside. Okay, flux is what? Q inside by epsilon naught. So there is no charge inside, so it's zero. Okay, this is first question. Now my another question is, find flux going outside. How much is flux going outside? So what to do? We know that total flux is zero. That means phi in plus phi out is zero. That means phi out is what? So minus phi in. What is phi in? We already calculated, right? If this electric field is E, then I already know what is phi in. Minus E into pi r square. So it is E into pi r square. Correct? No problem. Same way, another question will form. What is this question now? I will make one sphere. Okay, this sphere I made. Right? Now, what we can do in this one, but I have already told you this, so you can give me the answer. Okay, no issues. Shall I make it? No. Okay, this is R. So electric lines of force then. Electric lines of force are like this. Okay, I like this. This is E. So first is, what is the flux total associated with Gaussian surface? That's zero. Same way, what will be phi out? So we can say that phi total means is phi in plus phi out. Okay, and since this is 0, so we can say phi out is negative of phi in, and phi in already we calculated, already we have done. Okay, so E into pi r square. Okay, E into pi r square if its area I give is this, or rather radius I have already given. So no 4 pi r square, no 2 pi r square. That's why I am giving you all this. Okay, fine. General questions related to cube, charges inside place and all that, that I am not giving you. Okay, some different type of questions I am giving you so that you can recollect it what is happening, right? So what we will do, okay, this is one plate and its sides, you can say this is A, okay, and that is also A. The other side is also A. This is A, okay, and this is also A. And we have kept charge Q here. So question is asked from you, what is the flux through this? This is, what is that? Square surface. What is the flux through square surface? Flux through square surface. So what we know that this charge is placed in air and electric lines will be going in all directions. Okay, all directions. Symmetrically, it will be going in all the directions. Okay, so how to find how much is passing through this? So we will find out that this is square. We have to make one three-dimensional surface to enclose this charge first. Then only we can use Gauss law. So which Gaussian surface we can make? So we have to think about whose part is this? So we can say it's a part of a cube. It is a part of a cube. So we have to make a cube around it. So cube around it means how many surfaces? 6. So this can be one of the surface of that cube. So through this one flux will be 1/6. Okay. So flux through this square surface should be Q by 6 epsilon naught. Because total through cube is Q by epsilon naught, and this is one of its surface. So through this one will be Q by 6 epsilon naught. Okay. Remember that. Same way, same logic if we apply, I make one hemisphere and I say that here is charge I am keeping. Where? At the center. So how much is flux through this hemisphere? Flux through hemisphere is what? So first thing is you need to enclose it. You have to keep it inside the closed surface. So closed surface is which one? Close it. Like this we will close. Now it's a sphere. Okay, this is exactly in the middle. So half flux will be going here, half flux will be going up. So flux through hemisphere will be Q by 2 epsilon naught. Okay, in this same one, if we could have kept charge like this, and charge is here. Now this is already inside hemisphere. Here it was not inside. So we made inside closed surface. Here it's already inside. So here flux through hemisphere is Q by epsilon naught. But if it is outside, then it becomes 0. Okay. So if it's like this, and charge is here, then flux through this hemisphere is 0 because it's outside. Okay. Same way one more we will do. We make a cube. We will do it here. So this is a cube here. And suppose I kept a charge on this surface here. not on surface, in fact, on the edge. I kept the charge on the edge. Now the question is, how much is flux through this cube? You might have not done this like this. Okay, normally they'll be keeping it on this face. Okay, so but to close it, we make one more cube on this side. So we'll say that through this q by 2 and that is q by 2. Okay, through this one how much? Now this also has to be closed because this is not inside closed surface, three-dimensional object. So what we have to do? We have to keep one cube here and we have to keep one cube backside and one more cube on the other side. So through this one how much will go? Q by 4. Because to enclose this one you require 4 cubes on all sides. Okay, you require 4 cubes. So that is the reason why through this cube its flux will be Q by 4 epsilon naught. If the same one, if I am going to keep it on the vertex, then how much is flux through this one? Be Q by 8. Q by 8 epsilon naught, right? Q by 8 epsilon naught if it's here. Then you require 8 cubes to cover it. So all these questions we expect, okay, in the exam, they can ask us. This is Q by 8 epsilon naught. Okay. Then what are the applications of Gauss law? Gauss law we apply in finding out electric field due to wire, uniformly charged wire. The linear charge density we can assume as lambda. Okay, so uniformly charged wire and very long length it is having, and we want to find out electric field very close to it. Okay, maybe at distance r. Distance r, that means this is r. Then what we have to do? We have to make a Gaussian surface. What Gaussian surface we make? Cylinder. The Gaussian surface. Small Gaussian surface, such that we say that its length is dl. So this is Gaussian surface. And how is the electric field because of this wire? This wire's electric field is like this. This electric field. This side also. Okay. Same value of electric field, magnitude throughout this cylinder in all directions. Okay. So according to Gauss law, what we have? E dot ds equal to q inside by epsilon naught. Okay. Now which area is this one? Which is cut by this electric field lines? Entire curved surface. Entire curved surface because it's in all the directions. Not up and below because the electric field is not in that direction. Okay, so here area is along y-axis and electric field is along x-axis. So flux with this one is 0 and here is also 0. It is only linked with curved surface. Directly we can write E into 2 pi r dl, this curved surface area. Q inside, that means how much is the charge on this wire which is inside this? Now lambda is given. Lambda is what? Charge by length. Lambda is Q by L. That is also Q inside by length inside. How much is length? dl. So Q in is what? Lambda dl. We write lambda dl. Lambda dl by epsilon naught. dl and dl cancel. So E value is 2 pi lambda by 2 pi epsilon naught r. You have to remember, yes, we have to remember it. Certain times they will ask you a question on this one. One electron is orbiting around it. One electron is orbiting around it. They will give you certain information. Then they ask you, what is the radius of the orbit of electron or what is the electric field value? Okay, anything they can ask. Time period of that electron given giving the information regarding that. Okay. So this is here. Then whose electric field we find? Plane sheet. Electric field due to plane sheet is there. Let's make a plane sheet here. Okay. This way we'll not be able to. No. Okay, I only have to make it. All right. So plane sheet we have to make. Right, this is a plane sheet. And because of this plane sheet, again, you want to find the electric field very close to that, which may be at a distance r from it. Okay, this is uniformly charged. So what is the charge on this one? Plus sigma coulomb per meter square. Uniform charge density, charge by area is sigma. And we want to find electric field here. So what we'll do? Make a cylinder. And cylinder must pass through the point where you want the electric field. So this is half cylinder. Where is the remaining? The remaining is here. Okay, it's like this. In between, show you dotted lines. This is full cylinder. Why on both sides we have made? Because charge need to be inside it. And second thing is, whatever is the electric field value here, same is electric field value here also, because there is a charge here. So electric field is like this also, and electric field is like this also. Okay, this cylinder we have made, let's say its area is A, or rather radius is A. Okay, fine. What to do? Gauss law we have to apply. So Gauss law says E dot ds equal to charge inside by epsilon naught. Electric field we are finding. What is ds here? So electric field is like this. We have said outright. Like this. So which area is along the direction of electric field? This plane area and this plane area. So that only we will be writing. So 2E into this area. Pi A square you can write, or A itself you can write. Okay. Let it be A. A is pi A square. Okay. So 2E into A equal to Q inside. Now where is Q inside? Q inside is this. Okay. This is Q inside. This charge on this one. So what is this area? This area is A. The charge will be what? Sigma is what? Q by A. So Q is equal to sigma A. Sigma A by epsilon naught. Simple. A gets cancelled. So E value sigma by 2 epsilon. Like this we can do. So this direction also sigma by 2 epsilon naught. This direction also sigma by 2 epsilon. Is that simple? So this way we use Gauss law, okay, in calculation of electric field due to uniformly charged objects and infinite size objects, which is not possible through Coulomb's law. Okay, so that's all students today. We'll finish it here. Charges and electric field we discussed. Tomorrow's class, I'll be discussing about potential. So in that one, we'll cover up numericals on this as well. Okay, students, see you then tomorrow. Bye-bye. But before that, yeah, QR code I'll give you. Just scan it. It's taking too much time today because of longer class. Yes, finally. Okay, note it. Done? Completed, students?
Yes, sir.
Okay. See you then tomorrow. Bye bye.
Thank you, sir.